Chapter 5, Part A, Angle of Torsion, Sample Problem 1. If we have a hollowed cylindrical shaft which is fixed at one end and free at the other and handling a torsional torque of Q, dimension of the cylinder are provided to be a 20 millimeters inner radius, 30 millimeters outer radius, and the length of shaft is 1.5. Mhm. A question is what is the angle of torsion which will create a shearing stress of 70 megapascal at the inner surface of hollow shaft. The rigidity modulus is provided for steel to be 77 gigapascal. To approaching such problem, the very first step is calculating the polar moment of inertia for hollowed shaft. And if you do so, it just gives you J in hollowed sections. Hollowed cylindrical is a half of pi times C1 4 minus C2 to the power of 4. And if you do the mass, the outer radius is 30 millimeters as we uh, talk about it, and the inner one is 20 millimeters. So if you do the mass, it gives you 1.021 10 to negative 6 meter squared, meter to the power of 4. And at the same time, if we write down the equation for tau minimum, tau is Tc over J from formula, and how we know that that's tau minimum from the if you keep a closer look to the problem statement, it just says a shearing stress of 70 megapascal of the inner surface. If you remember the concept of torsion, as you go farther from center, you feel more stress. So it means the farther distances from center of the shaft experiencing more stress as if you're diving in a deeper water. So in that sense, C1, which is 20 millimeters inner surface, goes by tau minimum, and likewise C2, which is the outer diameter of 30 millimeters, goes by tau maximum. Mhm. And if we replace our value in the equation, that's C1, and which is 20. And the only unknown in this problem is a torsional torque of uh, T, which if you because tau is provided given, we just calculate the polar moment of inertia for the hollowed section, and if you replace to the equation, it just gives you almost 3600 newton meters of torsion. And when you have torsion, angle of twist is just TL over GJ. So torsional torque times length of the shaft over rigidity modulus, which is provided, and J, which we just calculated in previous slide. So if we have torsion, we have G, we have J, we have length of shaft, it's just gives you a numeric value in terms of radian. And if you want to convert that to degree, each 36 degrees, each 360 degrees, it's 2 pi radian, and that gives you a phi of a 3.91 degrees. If we want to solve this problem in an easier approach, uh, we can we can do that. I call that solution 2, which is a more direct solution toward the problem. So how is that? A more direct solution is just coming from Hooke's law in shear to compute the shearing stress. So Hooke's law in shear is tau is equal to G times gamma. So you can have tau mean, tau average, tau max. So because we are working in inner surface, we are working with inner diameter, inner radius, and that's C1. It just goes by minimum with the same fact. The closer to the center, experiencing less shear. So that goes by tau minimum. And in that sense, gamma minimum is uh, G over tau minimum over G. Tau minimum is provided, G is provided, and we get the value for gamma minimum. If now we come to geometry of the problem, and if we call that gamma, and this is again phi, and this is rho, so we can easily call that, observe that L times gamma minimum should goes by phi times C minimum and rho minimum, and rho minimum stands by C1 as a inner diameter. And if you do so, gives you a phi numeric value of L times gamma minimum over C, and that's a 1500 length of the shaft in millimeters over C1, because we need gamma minimum, and that goes by a, a gamma minimum. We just calculate gamma minimum to be 909 10 to negative 6. If you do so, it gives you the same exact value in radian, uh, which we had it in solution 1. Thank you.